For more information on SCTE, its training material or membership, visit scte.org. Amplifiers over the years, let's talk about some of the key components inside the amplifiers. So Lynn, I think between you and I, we can take this one and talk about passive plugins, diplex filters, and AGCs. First, let's talk about the passive plugin components. As mentioned, some of our more modern amplifiers have a lot of stages and a lot of components in them. But in order for them to work properly, the passive plugin components are very important. And when we talk about passive plugins, we immediately think about attenuators, cable equalizers, simulators, things like that. And we'll talk about each of those. But plugins come in a bunch of different shapes and sizes, and there are many points on the amplifier module itself to interact with these types of components. The amplifier schematics themselves are very important to understanding where the passive plugin components are relative to other components in the amplifier itself. Things like the amplifier hybrids that Deanna just talked to us about, the GaN and the gas amplifier hybrids and the preamps. There are different places in between those amplifier stages in both the forward and the return path to condition the signal as it goes into those amplifier stages. And for that, the amplifier schematics are very, very important. This one's fairly generic, but it also tells you where your test points are. This particular schematic indicates a 30 dB down directional coupler test point before the diplex filter and before the forward pad and equalizer station. We'll also talk a little bit about directional couplers or splitters because they are important in both the forward and the return to direct the signal to the various ports on the amplifier according to the design. So passive plugins come in a bunch of different shapes, sizes, colors, depending on the generation and the model of amplifier that you use. But it is very important to know where they fit in the amplifier according to the schematics for your particular amplifiers. The schematics and users manuals, I'll continue to reiterate, they're very important. If you don't have a copy of the user manual for the amplifiers used in your area, I would highly recommend that you get them. They'll often include the performance specs for various parts and components that go in the amplifier. So this is a different schematic of an amplifier, and you can see where the bidirectional test points are relative to the diplexes and your passive plugin components relative to your gain stages. But each of the passive plugin components does have some very important specifications that you should understand. Things like flatness and what the bandwidth measurement is for that particular component. This is for a signal director or a splitter that would go in here. But you can see this one is rated, for a flatness of 0.3 of a dB out to 1.2 gigahertz or 1218 megahertz. Other passives made in years past to support other amplifier lines may not be rated out to your particular bandwidth. As I mentioned, some of the plugins like JXP attenuator pads, and we'll talk more about those later, we've been using JXP attenuator pads for decades and they haven't really changed. However, over the years, they may have been manufactured and rated only to perform up to 750 or 870 megahertz. So understanding the amplifier model that you use, what the correct passive plugin components are, that's crucial information to get the best possible performance out of your amplifier. I put this in bright red because it's super important. Just because it fits in the slot doesn't make it the correct part. So let's talk about equalizers, simulators, and attenuators. Cable equalizers are intended to counteract the loss via attenuation of cable. So cable and the spacings between the amplifiers have attenuation. Now, attenuation is a function of frequency. The higher the frequency, the higher the attenuation. And that is not perfectly linear in that relationship from frequency to loss or attenuation. So the cable equalizer isn't perfectly linear either. These are some actual cable equalizer signatures at higher and lower values. So the top blue line here would represent about a 2 dB equalizer. And you can see it's relatively flat, but not perfectly flat. And then as you get into the higher values, like this 20 value equalizer here at the bottom, you can see there's actually a little bit of shape to it. Now that's intended to be the inverse of the, or the opposite of the shape of the cable to flatten that response based on attenuation. Similarly, cable simulators are intended to create loss that is in the same shape as the cable, so that the amplifiers can be more linear in their operation when it's short spacing between the amplifiers with a lot of loss, without a lot of loss. Attenuators are attenuators. They're flat loss across the entirety of their spectrum or their advertised bandwidth. Now, as I mentioned, this particular form factor, this JXP, has been around for a very, very long time. Not all of them, however, are rated out to 1.2 or 1.7 gigahertz. It's very important that you note in your user's manual or your specifications what the actual passband or flatness is. And I put this one here because this is a pretty standard JXP attenuator, but you can see that it is only rated out to 1 gigahertz or 1002 megahertz with respect to its loss and flatness. Any performance over 1 gigahertz may not be the desired response that you want from your attenuator. So it's important to match your amplifier models with the correct passive plug-in components. Now let's spend a little time with equalizers. Equalizers are also frequency matched to a specific bandwidth. In the table on the left, this is a cable equalizer chart for a 1.2 gigahertz amplifier. So all of the equalization values are measured across the entire spectrum from 1218 megahertz to 54 megahertz. Now, if our channel lineup only carries a 750 megahertz channel lineup through a 1.2 gigahertz amplifier, the equalization value of the equalizer may not match the amount of tilt that will be measured in our channel plan. So I have some blue arrows in these charts. Both of them are in 11 value equalizers. In the chart on the right, this is a 750 megahertz equalizer. So you can see in a 750 megahertz channel plan that only contains 117 channels, you can see that there is approximately 10 dB of equalization, the insertion loss at 750 equaling 1 dB to 11 dB of insertion loss at 54 megahertz. So you can see there's 10 dB of tilt from this 11 value equalizer. Now on those same channels with a 750 megahertz equalizer, you can see there's only about 7.7 dB of tilt associated with that equalizer, because the entire loss value of that equalizer is in fact 11 dB of equalization, but it's from 1.2 gigahertz to 54 megahertz. So when we install an 11 value equalizer into a 1.2 gigahertz amplifier that only has 750 megahertz of channel plan or active spectrum, there will be insertion loss of 4 dB on your highest channel. That's effectively taking away some of the operational gain of the amplifier. That's also very important to know when you're calculating the gains and losses of your amplifiers for setup reasons. So important to understand your equalization charts or the correct equalizers for your amplifier.